work? Are we recording? We are. Okay. So this is Physics 1A for February 22nd. This is technically our first real content lecture, and that means we're going to start from basics. We're going to talk about units, the units we're going to use, and what kind of things they measure. We're also going to then spend a good chunk of today talking about vectors. I hope I can get through all these topics on vectors, because if so, then we can start getting into some applications, such as the first condition of equilibrium and friction. So I think chances are we'll probably get to about here, talking about the scalar and cross products, and then we'll pick up with equilibrium next time. But if we have time, we'll keep going. All right, so units. Now, in this physics course, we're going to try to start from the complete beginning, the basics. I'm going to assume you don't really know anything. I know you've all taken at least one physics course, or you should have, but regardless, let's make sure we're all on the same page. So SI units. So in physics, as in any scientific field, one of the main things that differentiates our field from things like history and philosophy is that we all have to agree upon standards. And those standards we use to measure things. And when we measure things, we want to come up with units that we can all agree on. Now, there are kind of two types of units that we're going to talk about in this class. There's what's called fundamental units. And fundamental units are units that cannot be derived from anything else. They are, as far as we know, completely fundamental. And what those are basically mass, length, and time. These are the quantities. The units will be something like, for mass, we use the unit that we call the kilogram. For length, we use a unit that we call the meter. And for time, we use a unit that we call the second. Right? So those are our fundamental units in the SI system, the kilogram, the meter, and the second. In this class, we will still use things like feet. We'll use things, seconds. Seconds and minutes are the same, no matter what system you use. And for mass, we'll use pounds, but pound isn't really a measurement of mass. There's something called a slug, which is a measurement of mass. Okay, so let's talk about these individually and what they represent. So let's just start with, I guess the best one to start with really is time, I think, because it's going to kind of define the rest of the units. Okay, so time is a measurement of duration. It always goes in one direction. It is a scalar quantity. It doesn't have any kind of direction associated with it. It flows in one direction, but and historically, the way we measured time was by looking at some kind of natural oscillation or some kind of natural repetitive motion within nature. So, some of the... Let me get this to where I can actually see if you guys type. There we go. Okay, so what we have always done with time is we found something to count, some kind of regularity to count, right? And the first kind of simplest example of that would be the measurement of a day, right? A day is the time that it takes for the sun to go around the earth. That's an example. Okay, the time for the sun. Everything's working for you. That's a good page. So the time for the sun to revolve around the Earth. Now, the sun doesn't really revolve around the Earth, but as you observe it from our perspective, and if you were living, for example, in ancient Greece, and you wanted to describe what a day is, you'd say it's the time that it takes for the sun to go around once, because they thought that the sun revolved around the Earth, right? So that's a basic measurement of time. And then, of course, you can break this up into hours, and then you can break that up into seconds, right? You say there's 24 hours in a day, and then you say there's 60 minutes within an hour and 60 seconds within that. And so now you define what your second is, basically by using the time that it takes for the sun to revolve around the Earth, right? So this is a natural repetitive motion in nature, and it can provide us a way to measure intervals of time, right? So there's the second, the day, the hour. And we can, of course, subdivide the seconds farther if we want to into milliseconds. by just dividing by 1,000, or microseconds by dividing by 1,000,000, right? Now, this is a particularly Earth-centric type of definition for time, right? If we define time based on the time that it takes for our sun to go around our planet, then that's a very Earth-centric kind of definition. So there's other ways that you can do this. One way that is still somewhat kind of fixed to the Earth is you can use a pendulum. If you don't know what a pendulum is, it's a simple thing. You have like some type of a support from which you hang a string, right? And then you put a ball on the end that has some mass. And if you were to displace this by some distance, it would oscillate naturally back and forth and back and forth. And it turns out that the rate at which it oscillates is independent of the mass of the ball, and it really only depends on the length of this thing right here. So what you could do is you can construct a pendulum that specifically has a period of 1 second. So for example, if L is about equal to 25 centimeters, then what we call the period of oscillation, so T, the time that it takes for this pendulum to go from here to here to here and then back again, is about 1 second. Okay, so we call this a seconds pendulum, and this is one of the ways in which time was defined over the ages as well. Now, this again, it's a really good definition. You could very specifically construct pendulums to be a certain length, and this is a really good way to measure time, right? You could actually use this like a metronome. A metronome is another example of the same idea, Robert, yeah. You could easily use this to actually time things, right? Like, for example, if you were Galileo and you were trying to time how long it takes for balls to roll down hills so that you can measure the acceleration due to gravity, this would work pretty well because it has an accuracy of at least a second, right? Has an accuracy of at least a second because you can count the time it takes for it to go, and maybe even half second accuracy, right? Because you can figure out half of a swing, right? This is a pretty good clock in a way, at least a good timer. Maybe not a good like clock like a sundial that can tell you the time of day, but it's a good timer, good stopwatch, you might say, which is kind of what you would want in physics, yeah? So this is another definition that we used for time, but there's an even more modern definition that we use for time nowadays. So there's a problem with this one as well, which is, again, this really depends on the Earth, okay? Because the pendulum, its period of oscillation, it turns out that it's a function of gravity. The rate at which gravity flows determines how long it takes for this pendulum to oscillate. And if you were to go, for example, to the moon, where gravity is about 1/6 as strong, then the pendulum would not move. Well, it would have a longer period, basically. In fact, I guess I could tell you what the formula for this is, something that we're going to derive very, very, very much later in class. It's basically this. And maybe you remember this from your 2A class, I don't know. The period of the pendulum is given by 2 pi multiplied by the square root of the length divided by gravity. So gravity is still stuck inside of there, and that makes this kind of problematic. Suppose, for example, that we wanted to tell an alien civilization how long a second is. This wouldn't really work very well, right? So nowadays what we use are what are called atomic clocks. These are extremely accurate clocks, and the reason why they're extremely accurate is because they involve vibrations that exist within atoms. They involve basically the way in which an atom reacts when it's subjected to certain amounts of radiation. And the inner workings of how atomic clocks work require, an understanding of chemistry, but of course you can go read about these if you want to. But the basic idea is that certain types of atoms have natural frequencies of radiation, and you can use those frequencies to time things. These type of clocks have accuracy nowadays up to 1 in, it's like 10 to the 15, which if you don't know what 10 to the 15 is, it's basically 1,000 trillion, as if that helps. I don't know if it helps to say 1,000 trillion versus 10, but think about it this way. This basically means you have an accuracy up to 15 decimal places, right? So if the pendulum clock was able to do accuracy on the order of plus or minus half of a second, this would be plus or minus, 0.00. You have 15 zeros and then a 1, basically, right? So very, very accurate atomic clocks are. But the one thing that is consistent throughout all of these definitions is our definition of time relies on counting things that occur in nature, right? You either count the days, or you count the times of oscillation for the pendulum, or nowadays you count the number of oscillations within this atomic clock, right? But there you go. This is our definition nowadays of what a second is based on a certain number of vibrations of an atomic clock, basically. Okay, so that's our understanding of what time is there. Okay, I see a question. Someone says, "Is Physics 1620 later today at 6?" Jonathan, Physics 1620. I will put these recordings on YouTube, and that's it. If you're here for Physics 1620, that's great. You can stick around and you can watch the lecture. There's not a separate lecture at 6 p.m. Does that make sense, Jonathan? Okay, let's talk about length. Okay, so for the length, this has been something that's had different kind of definitions over time. In the English system, we measure feet. You know, the original definition of a foot would have been something like how big some king's foot was or something like that. Nowadays, when we measure length, the kind of most recent definition, I guess we could go back a little bit. One of the first definitions of what the meter was you basically took the Earth, right? And you got your equator here. And let's say you've got a prime meridian here. They basically said you take some fraction of that meridian, something like 1/10,000th or 1/100,000th, I don't know what the number was, and you called that a meter, basically. So that distance right there is 1 meter. That would have been kind of the original definition of what a meter was, right? More recently, we decided that we wanted to create fixed standards for length, and so the second definition was we have this bar that's kept at different facilities around the world that represents a meter. So you have a bar that's exactly 1 meter long, and you just say that's what a meter is. And if anyone needs to go and adjust, let's say you're a company that's making meter sticks. If you wanted to sell someone a meter stick, you'd need to at least go compare your meter stick to this piece of metal. And this is a piece of metal, and I think that's somewhat important. So this was our definition of what the meter was for a long time, up until I want to say the 1960s. I'm sure I'm getting that time wrong. But they decided this wasn't exactly the best way to define what a meter was. Does anyone have any idea what problems there might be by taking a piece of metal and defining it as a meter? Any idea? Shrinking and expanding, that's definitely part of it. I think you all probably know that metals tend to shrink if they cool, and they tend to expand if they get hot. So so that means that depending on what the temperature was, your definition of the meter may be off by, maybe not a lot, but maybe it's off by a micrometer, and maybe that matters in some type of measurement you're doing. Okay. Okay, so nowadays what we use, so I think there was one that used the wavelength of a krypton laser. I'm going to leave that one out because it's kind of connected to what we use now. So now what we use for the definition of length is we use the speed of light. So thanks to Einstein, maybe you have heard that all observers in the universe tend to measure the same speed of light. It's a universal constant. So we then can use that speed of light to measure what a meter is. So you basically just say it's the distance that light travels in 1 over the speed of light seconds, right? So 1 meter is equal to, here, let me put one. We define the speed of light to be c, right? So just to keep this simple, 1 meter is basically then equal to 1 over c seconds. Sorry, that's not right. That's not right. Maybe it is easier if I write it out as a number. 1 meter is the distance that light travels in 1 over c seconds. All right? 1 over, it's about 3 times 10 to the 8 meters per second. That's the speed of light. And the distance that light travels, and I think you get rid of the unit, right? You just say it's the distance that light travels in that many seconds. Oops. It's the distance that light travels in that many seconds. And I think an equal sign is probably the wrong thing to put here, but 1 meter is distance traveled by light in that many seconds. I'll just move this down here. Here we go. It's the distance traveled in 1 over think about it as like 1 over a billion or so, right? It's about the distance that light travels in a billionth of a second. A little more than that, but yeah. Okay. So that gives us a really nice universal definition of the speed of light, right? Just like for time, this gives us a nice universal definition for the meter, because everyone agrees on the speed of light and the distance traveled in that number of seconds, where a second is defined by an atomic clock. And again, this is the type of thing that you could communicate to an alien civilization. You can say, like, go get a certain type of atomic clock. A common one they use is cesium. Okay? And then we say, when a cesium atom undergoes about 1 billion oscillations, we'll call that a second. And then if you know what a second is, and you know what the speed of light is, just take the distance traveled by light in that many seconds. And now you've got very, very universal definitions of what time and length are there. Okay? All right. So, anyone have any questions? Okay, the last one here then is mass. So original definitions of mass involve water. So I think the first definition of mass is if you take a cube and you take that cube and you make it 0.1 meters on every single side, so 0.1 meters there, 0.1 meters here, and then a height of 0.1, so we'll put that over here. And then if you fill this entire thing all the way to the brim with water, then the mass of this is equal to 1 kilogram. Okay. So that's our original definition of mass. It's actually related to volume if you think about it. In fact, is that the definition of what a liter is too, right? Is that the definition of a liter? It's a box that's 0.001 meters cubed. So I think it's a liter of water, which is equivalent to a box that's 0.1 by 0.1 by 0.1, has a mass of 1 kilogram. So this also defines what the liter is, which is pretty nice. If you have 1 kilogram of water, it would occupy 1 liter. And that tells you something about density, right? Okay, that was our original definition. Call that definition number 1. Second definition was similar to this metal here. Basically, you create standards that are located at different places. You've got a cylinder, and you say, okay, this cylinder weighs 1 kilogram. You put these at different places around the world. There's kilogram standards in the United States. There's some in France. There's some in China. These are all over the world. So you have a reference standard for the kilogram. This is a fixed piece of metal. Okay, another piece of metal. I think in both cases, these were like platinum iridium alloys, as if that matters or if you find that interesting. Again, this is problematic because over time, these individual kilograms were actually losing mass. So after some number of years, they'd lost a few micrograms. And while it was still roughly a kilogram, you don't want roughly with science, you want exact, right? So you come up with a better definition. Now, this one gets really interesting. This is actually very, very recent that this was changed. So this was up until, I want to say 2018, maybe even 2019. We still used these pieces of metal to define what a kilogram was, but we just recently changed this. Does anyone know what we now define the kilogram based on? Quartz? What about quartz? No, we don't define the kilogram based on quartz. Maybe you're thinking of time. Number of atoms in a thing. That would certainly be a good way to do it, right? You could say, take some reference atom, such as maybe hydrogen or something like that, and say if you have a certain number of moles of hydrogen, that'll end up being exactly a kilogram. So that could be a good way to do it, for sure. You could use counting of atoms. And I know that was one of the ways that they actually thought about doing this, but that's not what they went with. Anyone else have any ideas? Isn't an electron made up of something else, or is it a proton? The proton is... okay, Kevin actually got the right answer. That's the right answer, Kelvin, sorry. So Andrew said, isn't an electron made up of something else? As far as we know, electrons are fundamental particles. You can't break an electron down into anything else. Yep. There's nothing it can really decay to either. In order to have something be made of something else, it needs to be able to decay. Protons, on the other hand, are made of quarks. Okay, so Calvin Avalar said, what about Planck's constant? And that is the right answer. Oops. Oh, there's the undo button. It's over there. So Planck's constant. If you don't know what this is, it is a constant. Okay, I think this is right. It's about 6.63 times 10 to the negative 34 seconds. Nope, not seconds, joule seconds. It is a very tiny quantity that you've probably seen show up in chemistry if you've taken chemistry classes. If you took something like Physics 2B, or if you took any type of physics where you started to talk about light and you got into talking about quantum mechanics, Planck's constant may have showed up as well. But it's a fundamental constant in physics similar to the speed of light, okay? And what you can do is, now this requires to talk about other types of units here, but if you look at this unit here, there's another way to write it because it involves joules, right? What's a joule? A joule is a unit of energy, and 1 joule happens to be equal to 1 kilogram, and then meters squared divided by seconds squared. That's what a joule is. So if you rewrite this, a joule times a second would then become 6.63 times 10 to the negative 34. Oops, 34. You get rid of one of the seconds, right? So you're left with kilogram meters squared divided by seconds. I think this ends up having units of... No, I'm wrong. Okay. So that's what Planck's constant is. And this is named after a scientist named Max Planck, or Planck. He's from Germany, and he is kind of the father of quantum mechanics. He figured out in certain systems it made sense to think of energy only coming in certain packets related to this constant, and he used that to solve a problem that was known as the ultraviolet catastrophe, or he was specifically talking about black body radiation. This is all stuff you're more than welcome to go read about. If you take Physics 1D, you absolutely will talk about this. But regardless, I'm getting way too into this. The whole point is the kilogram shows up there in the definition of Planck's constant, okay? And what you can do is you can basically use this to define what a kilogram is, okay? I have a video about this that I put up on Canvas. You can watch if you want to. It's pretty good. It's from Veritasium, if you know what that YouTube channel is. But he basically, this is a person that goes and show to a place where you can actually find out how they do this. But it involves electricity. It involves basically something that allows you to weigh something against an electric current, and more details, you eventually get the kilogram out of it. Now, one thing they had to do to make this work was they had to actually fix Planck's constant to a certain number. So you can continue the digits on this decimal here out to like 9 places, more if you want to. But they basically stopped it after 9 digits and said, this is what Planck's constant is. And then they used that to define what a kilogram is, okay? Now, again, this is a very universal definition of the kilogram. It's something we could communicate to alien civilizations. So in that sense, it's definitely good. Okay, so there's our fundamental units, right? And out of those fundamental units, at least for Physics 1A, we will be able to define all of the other units that we need. And I'll go into a few of those real quick here. What we call derived units. Already mentioned one of them. So derived units always take on some combination of these 3. Now, there are other fundamental units, okay? Maybe I should mention what they are. Let me just write in here what the other fundamental units are. Do some of you want to try to type some of them in chat? What are some of the other things that you think are fundamental units? Temperature? Yep, that's one of them. We measure temperature in Kelvin, right? Kelvin. Oh, that looks awful. Kelvin. What else? Texture? Mole? Yeah, mole is one of them. So quantity. Use a mole. Electric current. Yep. So current, which is measured in amps or amperes. And then candela is the other one. Kind of running out of units here, places here, but. And then candela, which measures brightness. More for astronomy. Mole, used a lot in chemistry, also used in physics 1b a lot, and 1c. Current, obviously, physics 1c. Temperature, physics 1b, right? And candela is like, I think it's stellar brightness. It's like how bright a star is, basically. I think lumens and candela can be converted between each other, Nigel. So it's a similar idea. Yeah. What else did you guys say? So people said things like, okay, I'm going to go down here and I'll write down all the things that were not fundamental units I'm going to put in this little list right here. So let's see, what did you guys say? So texture, I don't think we can measure texture. I think that's a relative kind of thing. Although we do measure hardness in terms of diamonds and things like that, and rocks. Okay, so derived units. Velocity, that's an example of a derived unit, right? Velocity is given by basically length divided by time. So I'm going to write these using, we're going to use length, L, M for mass, and T for time, okay? So length, mass, time, those are our fundamental units. So velocity is length over time, which would be meters per second. Associated with velocity, you've also got acceleration, which is the rate at which a velocity changes. Okay, and acceleration is going to be length divided by time squared. That's meters per second squared. What else did y'all mention? Someone mentioned volume and area. Okay, volume and area are also derived. So volume and area. Volume is going to be length cubed. Area is going to be length squared. So this is going to be meters cubed. But we also use something called the liter. And area, we've got meters squared. Or I think that it's the hectare, maybe, that we use in... a meter squared is better. I mean, it's always nice to just reference everything to the fundamental units. Okay. What else we got? Okay, so now we want to go through and kind of write down density. That's a good example. So density. Okay, density is like mass over volume, right? So you get mass, and we divide by volume, which is length cubed. So we measure density in like kilograms divided by meters cubed. Okay, and we can keep going. There's a lot of these. We've got force. We've got energy. We've got momentum. We've got pressure. I don't know. What else we have? That covers most of the things that show up on 1A, I think. So for force, we've got basically we use the Newton, and buoyancy is a type of force, Andrew. So force is going to be mass multiplied by length divided by time squared. That's going to be kilograms, meters divided by seconds squared. That's how we do force. Think F equals ma if you don't remember. Mass times acceleration, right? And this is also defined as the Newton. While none of the ones over here on the left have a special name, maybe volume has a special name, liter. Yeah, there's no special name for density. Force has its own thing, the Newton, right? Or in SI units, in non-SI units, we'd write the pound, which we'll see show up in some of the problems we'll do. For energy, you do mass times length squared divided by time squared. That's kilograms, meters squared over seconds squared, which is corresponding to 1 joule. For momentum, this one doesn't have a name. It's just momentum is just mass times velocity, right? So you take mass and then you multiply by velocity, which is mass divided by length, or times length divided by time, and so that's going to be kilogram meters divided by seconds. This is sometimes written as a Newton second in terms of like in rocketry when they're talking about the impulse of an engine. How well can the engine be projected upwards? They use impulse, and impulse is measured with momentum as Newton seconds. Can Planck's constant write in N? Capital N? What do you mean by N? What do you mean by N? I apologize, I need to turn something on here. Oh, can Planck's constant be written in newtons? Sure. So it would be... Oh my god, I apologize if this is loud. I think it will stop being loud. So, yeah, let's see. So Planck's constant is kilogram meters squared over seconds. So to get Newton out of that, the Newton would be kilogram meter over second squared. So you need to have a Newton times a meter times a second. Sure, there you go. A Newton times a meter times a second. That should work, right? Eliminate one of the S's, yeah. Okay. All right, pressure's next. This is getting pretty clumped in here, so let's move this down a little bit. So pressure is defined as basically force per unit area. So it's easier to start off over here and write down the unit we use for it. So it's force per unit area, which is like basically a Newton divided by a meter squared, which corresponds to what we call a Pascal. We're not probably going to use this unit in this class, but a Newton divided by a meter squared, what would that be? Well, we've got a Newton as meters times, or mass times length divided by time squared. So this is going to be mass over time squared, and then what, you got another meter here. Is that quite right? Whoops, not meter. Length. Is that right? Let me see. This is kg meters over seconds squared times meter squared. So yeah, you cancel one of these, and yeah, that's what you get. Okay. And there's a list of derived units. So this is the kind of stuff we're going to use in this class. We're going to talk about things that are measured in meters, things that are measured in terms of their mass, in terms of kilograms, time in terms of seconds, and then all of these derived units here. The ones we'll see show up a lot are going to be the Newton, the joule, and obviously all of these things. We'll talk a lot about velocity and acceleration in the first few weeks of this course. And from time to time, we'll use density. I think some of your homework problems involve density, area, volume, just to introduce like unit conversions and stuff, but there we go. Those are kind of part of the language of physics, is we need to have units, and anytime we use numbers, we got to have a unit with it, right? Okay, any questions? Okay. So let's look at something called dimensional analysis. So here I've defined that velocity is length over time, right? Acceleration is length over time squared. This is part of dimensional analysis. Oops, I didn't mean to do that. I think it's okay. All right. Dimensional analysis is where you kind of compare two different sides of an equation. So let me write down an equation and say what I mean by this. So an equation you may be familiar with from, if you took a physics course before, is the way in which you find the final velocity of an object if you know what the initial velocity of the object was, and you also know the acceleration of the object and the time for which it was accelerating, right? This equation, where the velocity, v represents velocity, t obviously represents time, and a represents acceleration. We can kind of verify that this equation is dimensionally accurate by doing the following. So we're going to look at the dimensions of the left side here. Sometimes the way this is written in some books is by doing something like this. That means find the dimensions of this, which in our case, dimensions of velocity are length divided by time. On the right-hand side, the dimensions of initial velocity would also be length divided by time. The dimensions of the acceleration would be length divided by time squared. And the, I don't know what the right way to write this is, but acceleration is length per time squared, and then time has obviously dimensions of time. So what we end up with is, on the left-hand side, we have units of length over time. On the right-hand side, we have units of, well, length over time as well. One of these t's cancels out here. We don't really worry about saying that there's two of these on the right-hand side. We just say, okay, this is length over time, and we're adding to that length over time. That's perfectly fine. So you get length over time on both sides. And so what we would say is that this equation is dimensionally accurate. This is something you can do when you're solving your homework problems to kind of verify that the answer you got made sense. It's something I'm going to bring up a lot in this class is how if you're worried that you're doing something wrong, you can use dimensional analysis to figure it out. Just to show you a simple example of how that might happen, there's another equation. I'll write it over here that looks like this. Again, I'm using kinematic equations because I kind of assume you probably have seen these before. Now these equations, they don't look the same, but they have a lot of similar properties, right? They both involve initial velocity, and they both involve acceleration. The difference in these two cases is that on the left-hand side we have distance. So to get distance, you need to have a velocity times a time or an acceleration times a time squared. But let's say while you're doing your homework, for some reason you forget and you mix up the two equations, as is a pretty common thing to do. And maybe you just, as you're writing your equations down, you write this down. You write, because you're kind of mixing them up, right? This is at squared and that one's at, you just forget. Suppose you write this one down. You could ask the question, does this equation make any sense? Can we use this equation to make any sense? And you should be able to see pretty quickly that you can't, because you've got over here, you've got length over time, you've got length over time, and then you've got length over time squared multiplied by time squared. And unfortunately what you end up getting is length over time equals to length over time plus length. And this is something that's not allowed. Oops. You can't do this. If I have 1 meter per second and I want to add to that 5 meters, this doesn't mean anything. This is not equal to anything, right? I can't take 5 meters and add a meter per second, right? I can't take 5 pounds plus 2 meters. That doesn't mean anything, right? You've always got, anytime you add, these two units have to be the same, right? It's kind of similar to the way it works in algebra, right? If I have 2x plus 2y, and I say, can you simplify this? There's not really anything you could do. I mean, maybe you can factor out a 2 or something like that, but I can't add x plus y. If instead I say 3x plus 7x, then you know that this is 10x, right? Now just replace x with meters, or meters per second, whatever you want to do, and it tells you that you can only really add units when they're the same. You can multiply units when they're different. That's okay. That's defined. But you can't add. You can't subtract. Okay? Alright, so that's how dimensional analysis can be helpful. I don't know if any of you will actually do this. I don't know if while you're doing your homework you're going to check to make sure the units work out, but I will during class while I'm going through problems, and I'll encourage you to do so as well. You're always going to want to check that your units make sense. Okay? And that might not mean checking the first line. It might mean, more likely, checking the last line of your equations and making sure that all the units make some kind of a sense. All right, so let's look at one way in which this can be kind of powerful. Let's look at like an actual kind of physics system that we can use dimensional analysis to think about. So suppose I ask the following question to you. Let's say that I've got a ball and I want to drop it, okay? And I ask the following question. So let's say that I take a ball and I hold it up to some height above the ground, and let's define that height relative to, here's the ground. I define the height of the ball above the ground to be h, and I tell you that we're on the planet Earth, so we know that gravity is going to tend to draw this ball to the Earth when I let it go. And so let's say we let it go, so the ball is released from rest. And if it's released from rest, it's then going to take some amount of time to fall down to the ground here. It'll fall down and it'll hit the ground, right? It's going to take some amount of time to fall. If I hold it up to a certain height, and let's say it takes 1 second, for example, and maybe I hold it up to another height and it takes 3.5 seconds, right? So the question is this. How much higher should I drop the ball from if I want to make it take twice as much time? Okay, so that's the question that we're going to work with here. So this is the setup, and the question is, how much higher Okay, that's the question. How high should you drop the ball relative to the initial height that you dropped it from, that we call h, so that it takes twice as long to hit the ground? Now I want you all to think about the answer to that. And I want you to, when you feel confident, type what you think the answer is in the chat. Should it be 2 times as high, 3 times as high, 4 times as high, 5 times as high? What should it be? Does the question make sense? How high should you drop the ball so that it takes twice as long to hit the ground? Does the question make sense? And I'm not looking for explanations. We'll do those later. The question is for you to just predict, how high should it be? Should it be 2 times as high, 3 times as high, 4 times as high? What is your intuition? I don't necessarily want you to get it right either. I just want you to tell me what your intuition is. What is the first thing that you think the answer is? Okay, so I see one person said not twice. One person said 2 times. One person said 4 times. I am not here to judge whether you get this right or wrong. I just want to see what you predict the answer to be. And then we're going to go through and we're going to use dimensional analysis to answer it. Okay, someone says x squared as high. Okay, so here's the way that we're going to do this. A lot of people are saying 4 times. Let's see if you're right. So here's how we're going to do this. Instead of using known equations for the time that it takes for the ball to fall, in fact, I've actually written one of them on the pages already, we're instead going to look at it this way. We're going to use dimensional analysis. So we're going to say, what could it depend on? What factors does the time to fall depend on? What do you all think? Okay, one person says gravity. We'll call that G. What else? The height? Absolutely. We'll call that H. Anything else? The mass? Okay. Now, one thing I'm leaving out of this, we're going to assume that the ball is being dropped over a short enough height such that air resistance does not affect it, okay? So, and we're also going to assume the ball is made out of, something that's hard, like a basketball would be fine, a baseball would be fine, a tennis ball would be fine. Something that's not so light as to be affected by drifts of air, right? We're not going to use, like, a crumpled up piece of paper. Okay, if it's on rest, we did say, Angie, that it starts from rest. We're specifically saying it's going to start from rest, but you're absolutely right. If we threw it upwards, it would take longer. If we threw it downwards, it would take longer. Okay, drag force could play a role, Haidar, but we're going to assume the wind is not going to affect it, right? Okay. We're just going to assume it's a type of ball. It's a short enough distance, right? Now, if we drop something off the top of a really tall building, of course, drag force matters, right? Okay, Hudson says only height and gravity matters. Okay, let's see what we get here. Okay, so how much time do we have left? Okay, 2:51. We're fine. So I think we can get through this. So the way I'm going to write this down is I'm going to use proportionality. I'm going to say the time that the ball takes to fall. I'm going to use this proportionality symbol, and then you all gave me these factors here. So we've got gravity, we've got height, and we've got mass. Now we know from what I said before, we're not going to find the answer by adding the acceleration due to gravity plus the height plus the mass. So we know the only thing we can really do with these things that have different types of units is to multiply them by each other. However, if we just multiply them by each other like this, it's not gonna work out, right? And we can prove that by writing in the units, as we'll do in a second. So instead what I'll do is I'll say G is gonna have to be raised to some power that we'll call X. H is gonna have to be raised to some power that we call Y. And then the mass will be raised to some power that we call Z. And our goal basically is to figure out what those powers are. What is X, what is Y, and what is Z? What are all these things? That's our goal. What are the powers that we raise these to get time, basically? I don't care about factors. All I care about is proportionality here, right? Okay, so we use our dimensional analysis, right? We know that time has a symbol that we call t. We know gravity is a type of acceleration, so it has units of length over time squared. We have to raise that to the x power. The height has the units of length, and we raise that to the y power. And then mass has units of, mass. And we raise that to the z power. Now we can actually figure out x, y, and z exactly from this equation here, because there's a couple things that we can notice. We have L to the x multiplied by L to the y. L is length. There are no links that show up over here. So what I could say is that it must be the case that x plus y is equal to what? I want to make sure that I don't get any links over here, right? So x plus y has to be equal to what then? How do I make sure that I eliminate these L's here? For example, if I told you that x was equal to, if I told you that x was equal to positive 3, let's say, what would y need to be to guarantee that you don't end up with any links over here? I see Andrew saying it's a multiply by 1 over L. Sure, because if I write L over L, I get rid of the lengths, right? So how can I say that in an equation? Maybe that's too hard to think about. Maybe we think about the other one first. What does z have to be equal to? What does z have to be equal to? 0. Okay, you guys got that one really fast. That's good. We know that z has to be equal to 0 because there's no masses that show up on the left-hand side. So by the same logic, L to the x times L to the y better give us something similar, meaning, what if we wrote it like this? What if this is simpler? We have t squared, oops, that's not right. We have 1 over t squared, that's raised to the x power, and then we have L, when you have L to the x and L to the y, you basically do L to the x plus y. And we already kind of know what m is, but that's fine. Does this help you to think about what it is? What is x? I see someone actually wrote the right answer. D. Sanchez said, it should be the case that x is equal to negative y. Or rearranging that, you get x plus y equal to 0. So that's the answer. Basically, since you have time on the left-hand side, L raised to the x plus y, this has to be a 0. And this has to be a 0. Right? Or else you'll be left with lengths, and we only need time, right? So there's one thing left, and this is the one we can figure out exactly. What does the power of x need to be in order to make sure you get time over here? What does this power of x need to be so that you get t to the first power? So you have t to the 1 here. We have 1 over t squared here. What does this power of x need to be to guarantee you get t to the 1 on the left-hand side? Negative 1/2. That's right. Negative 1/2. Because if we have negative 1/2 right here, it'll flip this to t squared, and then the 1/2 will make it a 1, right? Can everyone see that? So we found what z was. We found what x was. And then we can use this equation to say that negative 1/2 plus y equals 0, or that y has to be equal to positive 1/2. So let's put this all together. That was our original equation, right? Let's just plug everything back in. So we end up getting t is equal to g to the positive, g to the x, right? So g to the negative 1/2 multiplied by the height that it's dropped from to the positive 1/2, because that was our y factor. And then the mass to the 0th power. Now, I wrote an equal sign here. That is not correct. I'll erase that. It's not equals. We're still in the proportionality world. So, written in a way that's a little bit easier to read, what this would say is we have g down here in the denominator, we've got h up here in the numerator, they're divided, and there's a square root. And that is our proportionality for this system. Here, let's move this up here a little bit so we can actually go back to our original question. So that's the answer we got. Square root of h over g is going to tell us, proportionally at least, how long the time is. So the original question was, how high should you drop the ball so that it takes twice as long to hit the ground? And those of you that said 4 times as far, you're right. Because if you quadruple the h, you take the square root of that, you get a 2, right? And if I plug in here square root of 4h over g, I leave gravity the same, then that's going to end up giving me double the time, right? I don't know what the right way to write this is. This is 2 times time, something like that. Okay. Where did we get x to the negative 1/2 power? So you can just look at this portion right here. if you want to figure out where that came from, Andrew. I have t squared. I've got an x up here. And I want to make it so that I get t to the first power. So you can basically just solve this equation for x. Just that piece. And the only one that'll give you a 1 over here is if I put x equal to negative 1/2 right here. Can you see that? Okay. So there we go. Without knowing anything about the actual laws of physics, other than that gravity is a thing, which honestly everybody knows about gravity from the moment they're like 2 years old. Maybe you don't know what the value is, you just know that there's an acceleration due to gravity. Maybe you don't know that it's a constant acceleration, but you've all taken a physics class. The point is that we were able to derive an actual, this is a legitimate physics expression, without actually doing any real physics, right? We just looked at the units. Now, if we were at school, I would do a demo where I'd roll a ball down a hill in a track in the classroom, and I would show to you that this actually works. Because it turns out that you don't need to just drop the ball. You can also roll it down an incline. You get exactly the same effect, where you can replace the height with the length of the incline if you want to. Anyway, I can't really show you that demo where we are now, but it's something you can kind of try for yourself at home if you want to. Okay, so anyone have any questions before we take a break? Good place to stop. What we'll do when we come back is we'll start talking about vectors. All right, what time is it? 3 o'clock exactly. So we're going to take a break until 3 p.m. And I'll stop the recording.